Okay, today's video is over improper integrals with two infinite bounds. Now, this is similar to my last video over improper integrals with one infinite bound. However, as you could probably assume, these integrals feature two infinite bounds. And the process of solving these integrals is similar to the last, slightly different. It involves splitting the integral. I'd like to give you a quick refresher on what an improper integral is. It is an integral featuring a vertical asymptote present within the interval, or it is an integral featuring one or more infinite bounds. Essentially, it can't be solved in its current state, and it has to be solved using limits. Okay, so the process for solving an improper integral with two infinite bounds is quite simple. First, of course, you have to identify your integral as an improper integral. And as I said earlier, if it has a vertical asymptote present between its interval, which we'll go over in a future date, or if it has one or more infinite values in its bounds, then it is improper. And this over here is just the general term for an improper integral with two infinite bounds. You can see that we have both infinity and negative infinity. So if given this integral, this improper integral, you're going to want to split your integral into two pieces. Now, this is just a law of integrals in which you can split a given integral, let's say the integral from b to a of f of x dx, as 0 to a f of x dx plus b to 0 f of x dx. And this is exactly what we're doing with our improper integral. And so we're splitting into two, and then we're taking the limit as n approaches infinity of our upper bound and the limit as approaches negative infinity of our lower bound. So we're essentially using the same process we did to solve improper integrals with one infinite bound, except we are now splitting our integral into two separate pieces and then individually solving it. One thing I'd like to note is that the value at which you split your integral does not really matter, so long as the bound is featured in both integrals. You may want to split it at the vertical asymptote if your function or your integrand has a vertical asymptote. However, that's not going to be discussed today. As I said, it's going to be discussed maybe in my next video or so. Okay, so this is practice problem 1. We're told to find the infinite integral, or the improper integral, from negative infinity to infinity of 6 over 1 plus x squared dx. And immediately, you may recognize this as an arctan function, or deviation of an arctan function, because the derivative of arctan of, let's say, x can be represented as 1 over 1 plus x squared. And that looks awfully similar to our integrand over here. And so it's likely that this is the derivative of arctan x, or arctan something. So we'll begin by splitting our limit, or splitting our integral into two separate pieces, one consisting of the limit as n approaches infinity of, let's say, n to 0 of 6 over 1 plus x squared dx, plus the limit as, let's say, m approaches infinity, negative infinity, I should say, of 0 to m 6 over 1 plus x squared. And so we're just splitting our integral into two separate pieces, and we are taking the limit as n approaches infinity or m approaches negative infinity, respectively, of each separate piece, such that we can solve it. And what we're going to do at this point is solve each individual function. We'll begin by solving the left side, the left term. Just focus on our integral real quick. If we were to factor out 6, we'd end up with the integral from n to 0 of 1 over 1 plus x squared dx. And this is, of course, arctan. And so we end up with our left term equaling 6 arctan, 6 arctan x from, I believe, n to 0. And I forgot that we have to take the limit, of course. So I'll write that over here. And we'll solve this in a moment. In the meantime, let's try to find the value of this function over here, or this term over here. If we can implement the same process in finding this, and we'll come with the outcome of the limit as m approaches negative infinity of 6 arctan x from 0 to m. And from here, we can begin substituting in our values and in 0. If we take a look at the left side, we can see that we end up with the limit as n approaches infinity of 6 arctan n minus 6 arctan 0. And I believe 6 arctan 0 is equal to 0 because arctan 0 is 0, if I recall correctly. And so we can erase that function. Plus the limit as m approaches negative infinity of 6 arctan 0, which is of course 0, minus 6 arctan m. Okay, and as I said earlier, 6 arctan 0 is 0, and so we can erase that. And we end up with the limit as n approaches infinity of 6 arctan n minus the limit as n approaches infinity of 6 arctan m. And the reason we're subtracting the 2 is because of this negative sign over here. Okay, and from here we can begin substituting in our n and our m. 6 arctan infinity is equal to 6 times the square root, 6 times pi over 2. Now keep in mind, when we take the limit of something, we aren't really substituting in our value as it approaches some other value. What we're really doing is finding the value as n approaches infinity. However, in this sense, it can be represented as 6 arctan infinity. And arctan infinity, or I should say the limit is n approaches infinity of arctan n, is pi over 2. That's just something you have to know. And of course, we're multiplying that by 6, so we end up with 3 pi. Now, the limit as n approaches infinity of 6 arctan m, the limit as m approaches negative infinity of 6 arctan m, can roughly be represented as 6 arctan negative infinity. 6 arctan negative infinity is 6 times negative pi over 2. And so what we're doing now is we are taking the difference between 3 pi and negative 3 pi, and we end up with 6 pi. So the value, or the integral from negative infinity to infinity of 6 over 1 plus x squared dx can be represented as 6 pi. That is it for practice problem 1. Okay, this is practice problem 2, and in fact, the last practice problem for today. We're told to find the value of the integral from negative infinity to infinity of x squared over 1 plus x cubed squared dx. So this is, as you could hopefully identify, an improper integral, one with 2 bounds, in fact. So what we're going to do is we're going to split it, and we might as well split it from 0 to infinity and negative infinity to 0, as that's just the simplest way of splitting this. So we can say that our integral is equal to the limit as n approaches infinity of 0 to n x squared over 1 plus x cubed squared dx, plus the limit as m approaches negative infinity of m to 0 x squared over 1 plus x cubed squared dx. And so from here we have to integrate. What we have to integrate is the integral of x squared over 1 plus x cubed squared dx. And hopefully you'll be able to immediately recognize this as an integral solvable using u sub, because if we were to integrate this integrand, we'd end up with a composite function, meaning that u sub's applicable. If you're unfamiliar with u sub, I've made a video on it in the past, so watch that if you feel you're unfamiliar with u sub. But we can begin by assigning 1 plus x cubed to u, and therefore the derivative, du, is equal to 3x squared dx. Now, what's beautiful about this is that 1 plus x squared is present in our integrand as well as x squared, but 3x squared is not. So we have to manipulate our equation, and we end up with 1/3 du is equal to x squared dx. Now notice how x squared dx is present in our integrand of both integrals, meaning that we can easily substitute all our values in. So first, let's begin by substituting in our value for the left-hand term. Let's substitute u in for the time being. We end up with the limit as n approaches infinity of 0 to n x squared over u squared dx. Now, this isn't solvable in its current state because we have a u in the integrand, but we're integrating with respect to x. So we have to substitute in our 1/3 du in place of x squared dx. And so I'm going to do that. I might as well throw this 1/3 over here. And so that is our left-hand term. It's going to be the same as our right-hand term, the only difference being the bounds, or the boundaries, whatever you want to call them. Okay, and so from here, we just need to integrate 1 over u squared. 1 over u squared is equal to negative 1 over u. This is just, this is of course because we can model 1 over u squared as u, -2, and therefore we end up with negative 1 over, or negative 1 times u to the power of negative 1, and that's equal to negative 1 over u. That's just a quick reason as to why I'm doing this. So we can integrate, or we can take the antiderivatives. I'm not a fan of this color, so I'm going to switch. Okay. And so we might as well substitute out the 1/3. I forgot to put this over here. But we're going to begin by substituting out the 1/3, the limit as n approaches infinity of negative 1 over u from n to 0, or from 0 to n, plus the limit as m approaches a negative infinity of negative 1 over u m to 0. And so we can begin. I also do not like this color. Sorry. Okay. From here, we can substitute in our values, n, 0, m, and we can equate this to 1/3 limit as n approaches infinity of negative 1 over n minus, okay, sorry, I made a mistake, kind of. Before we begin by substituting our values, we're going to substitute in our values of u, because I haven't yet done that. So really, we can equate this to 1/3 the limit as n approaches infinity of negative 1 over u. However, u is equal to 1 plus x cubed, so we'll throw that in now. From 0 to n, plus the limit as m approaches negative infinity of negative 1 over 1 plus x cubed from m to 0. Okay, so now we can begin substituting our values. We'll equate this to 1/3 the limit as n approaches infinity of negative 1 over 1 plus n cubed minus 1 over 1 plus, sorry, this should be a plus because we are taking the difference of a negative, so we're adding them, plus 1 plus x over plus 1 over 1 plus 0 cubed, which is of course 0, meaning that really we're just adding 1 because we're taking the difference of negative 1 over 1, so we might as well just add 1. Plus the limit as m approaches negative infinity of negative 1 plus 1 over 1 plus m cubed. And so from here, we can begin taking the limit of these two terms. I'm going to have to make a bit of room, so I'll erase this over here, as well as this. And I will continue on this side over here. So all we need to do now is substitute in our, or not really substitute in our values, but take the limits of our values. So we end up with 1/3 the limit as n approaches infinity of negative 1 over 1 plus n cubed. That can really be modeled as negative 1 over 1 plus infinity cubed, which is 1 over infinity. Now, 1 over infinity is equal to 0. Just as infinity over any other value is equal to infinity, this is going to be equal to 0. So this term over here is equal to 0. Now this term isn't affected by the limit as n approaches infinity. So that's just 1. Plus the limit as m approaches negative infinity of -1. So hold on, I don't know what happened over here. 1/3 m minus 1 plus the limit as m approaches negative infinity of 1 over 1 plus m cubed. Now, that can be modeled as 1 plus m negative infinity cubed, which can be modeled again as negative 1 over infinity, but negative 1 over infinity, just as 1 over infinity, is equal to 0. So this term again can be omitted because it's equal to 0. And so we end up with 1 minus 1. One second. We end up with 1/3 1 minus 1. 1 minus 1. And this is equal to 0. So that was a bit difficult, but the integral from negative infinity to infinity of x squared over 1 plus x cubed squared dx is equal to 0. That is all for today's video. I hope you enjoyed it. If you have any suggestions for future videos, please put them in the comments below. Thank you.